Vehicle dynamics refers to the dynamics of vehicles, here assumed to be ground vehicles. Vehicle dynamics is a part of engineering primarily based on classical mechanics. This article applies primarily to automobiles. For single-track vehicles, specifically the two-wheeled variety, see bicycle and motorcycle dynamics. For aircraft, see aerodynamics. For watercraft, see hydrodynamics. Components, attributes or aspects of vehicle dynamics include automobile layout, electronic stability control, steering, suspension, traction control system, aerodynamics. Specific some attributes or aspects of vehicle dynamics are purely aerodynamic. These include automobile drag coefficient, automotive aerodynamics, center of pressure, downforce, ground effect in cars. Geometry specific some attributes or aspects of vehicle dynamics are purely geometric. These include Ackermann steering geometry, axle track, camber angle, caster angle, ride height, roll center, scrub radius, steering ratio, toe, wheelbase. Mass specific some attributes or aspects of vehicle dynamics are purely due to mass and its distribution. These include center of mass, moment of inertia, roll moment, sprung mass, unsprung mass, weight distribution. Motion specific some attributes or aspects of vehicle dynamics are purely dynamic. These include body flex, body roll, bump steer, Bundorf analysis, directional stability, critical speed, noise, vibration, and harshness, pitch, ride quality, roll, speed wobble, understeer, oversteer, lift-off oversteer, and fishtailing, weight transfer and load transfer. Yaw. Tire-specific some attributes or aspects of vehicle dynamics can be attributed directly to the tires. These include camber thrust, circle of forces, contact patch, cornering force, ground pressure, Pace's magic formula, pneumatic trail, radial force variation, relaxation length, rolling resistance, self-aligning torque, slip angle, slip, steering ratio, tire load sensitivity. Roadway specific some attributes or aspects of vehicle dynamics can be attributed directly to the roads on which they travel. These include banked turn, cross-slope, drainage gradient, and cant or super-elevation, road slipperiness and split friction, surface roughness, international roughness index, profilograph, texture, driving techniques. Driving techniques which relate to, or improve the stability of vehicle dynamics include cadence braking, threshold braking, double declutching, drifting, handbrake turn, bootleg turn, heel and toe, left foot braking, opposite lock, Scandinavian flick, ski, wheelie, analysis and simulation. The dynamic behavior of vehicles can be analyzed in several different ways. This can be as straightforward as a simple spring mass system, through a 3-degree of freedom bicycle model, to a large degree of complexity using a multi-body system simulation package such as MSC Adams or Modelica. As computers have gotten faster, and software user interfaces have improved, commercial packages such as CASM have become widely used in industry for rapidly evaluating hundreds of test conditions much faster than real-time. Vehicle models are often simulated with advanced controller designs provided as software in the loop with controller design software such as Simulink, or with physical hardware in the loop. Vehicle motions are largely due to the shear forces generated between the tires and road, and therefore the tire model is an essential part of the math model. The tire model must produce realistic shear forces during braking, acceleration, cornering, and combinations, on a range of surface conditions. Many models are in use. Most are semi-empirical, such as the Pace Car Magic Formula model. Racing car games or simulators are also a form of vehicle dynamics simulation. In early versions, many simplifications were necessary in order to get real-time performance with reasonable graphics. However, improvements in computer speed have combined with interest in realistic physics, leading to driving simulators that are used for vehicle engineering using detailed models such as CARSIM. It is important that the model should agree with real-world test results. Hence, many of the following tests are correlated against results from instrumented test vehicles. Techniques include linear range, constant radius understeer, fishhook, frequency response, lane change, moose test, sinusoidal steering, skid pad, swept path analysis.